Welcome to the deep dive. We are sitting on a truly enormous stack of sources today, all focused on cutting-edge materials science, really the future of fabric. If you're looking for a crash course in how the clothes on your back are about to be completely redefined, well, you're in the right place. We're taking a deep dive into the fascinating, and I mean explosive, collision of nanomaterials and textiles.
It really is a collision of eras. If you think about it, they're ancient. They're these conventional fiber-based materials that we've been using for, what, thousands of years? They're the definition of tradition.
And then on the other side of that, you have nanomaterials. I mean, that's the modern buzzword, right?
Yeah.
It's the absolute cutting edge where everything is engineered at the atomic level.
Exactly. And the scale of interest in, bridging these two worlds is just staggering. We ran a search on Google Scholar just a couple of months back in October 2024.
Okay.
And combining nanomaterials and textiles, we found about 207,000 publications.
207,000 papers. Wow. That is a massive amount of research to try and get through.
And it's growing fast. We've seen this remarkable, almost exponential growth just over the last 15 years. So it confirms this is not a niche area. This is a critical, emerging scientific focus that is going to reshape manufacturing. Our mission today is to, well, cut through all that complexity, pull together what those papers are telling us, and really reveal the key applications, the challenges, and the disruptions researchers are focused on right now.
Okay, so let's start there. The big question. What is the point of applying these incredibly modern, sophisticated materials to something as, simple as cotton or polyester? Let's talk about the transformative power of nanofunctionalization.
The core idea here, the value proposition, it isn't just about small improvements, it's about total disruption. By adding nanomaterials to conventional textiles, you can create new functional products. You can give them enhanced or, in many cases, completely new properties they just couldn't have before. You're essentially turning a passive material into an active high-performance system.
Okay, that makes me think immediately of safety. What are some of the most practical, maybe even life-saving enhancements that we're seeing in the research?
Protection and safety are definitely a key starting point. We see textiles getting these really crucial features like antimicrobial protection and flame retardancy. This is often done by applying what are called nanoparticular finishing agents.
Okay, hang on. Nanoparticular finishing agents. For those of us who aren't materials chemists, can you paint a picture of what a sol gel-based finish actually feels like? Are we talking about a plastic coating on a shirt?
Right, great question. And no, not at all. That's the beauty of it. A sol gel process creates this incredibly thin, almost glass-like metal oxide layer that's really durable, but it keeps the fabric's original texture and breathability. Because the particles are so tiny, they just integrate seamlessly. They provide those properties like stopping bacteria from growing without making the textile stiff or uncomfortable.
That is fascinating. So that's kind of the basic level of enhancement. But the research goes way beyond that into really specialized safety. I was particularly struck by the work on radiation protection.
Yeah, this is where you see that radical shift. The source's detailed methods for creating radiation protective textiles, specifically for things like X-ray garments. They do it by embedding heavy particles like lead and tin directly into the fibers themselves.
So wait, instead of wearing one of those super heavy, bulky lead aprons you see in a hospital, which are thick and just don't bend, the protective material is actually woven into the fabric itself during the spinning process.
Exactly. It's a complete reimagining of shielding. You can create garments that are lighter, much more flexible, and probably a lot more comfortable without losing that protective quality.
And beyond just pure safety, the research also looked at protection in terms of visibility and identification. What were they doing there?
They're getting some really remarkable luminescent effects. This involves applying things like phosphorescence inorganic particles or even fluorescent carbon quantum dots to the fabric, so you get textiles that can literally glow under certain conditions.
And I saw a really specific high-tech application for ID purposes. They're using filaments loaded with persistent luminescent nanoparticles. It sounds like it goes way beyond just making a safety vest brighter.
Oh, absolutely. The fact that the luminescence is persistent allows for covert identification and tracking, not just in the visible spectrum, but also, and this is critical, in the infrared spectrum. So think about high-security uniforms or advanced parts that can be tracked precisely and invisibly using this built-in nanosignature. It's like anti-counterfeiting woven into the very fiber.
That level of precision and control becomes even more critical when we shift to advanced medical uses. I mean, this part of the research really starts to feel like science fiction.
It really does push the boundaries. One big area is developing carbon nanodot-loaded PLA nanofibers. Now, PLA is polylactic acid. It's a biodegradable, biocompatible polymer. That makes it a perfect scaffold for really specialized medical uses. We're not just talking about sterile gauze here. We're talking about highly targeted therapies.
Can you elaborate on the drug delivery systems they're designing? Because I saw some pretty intense chemistry you mentioned there.
Yeah, this is probably one of the most sophisticated applications we saw. Researchers are creating polyvinyl alcohol or PVA nanofibers that contain these cationic lipid surene complexes.
Wait, Serene, for anyone hearing that for the first time, are we actually talking about RNA interference, like a key component in gene therapy being delivered through a thread?
Precisely. They're using a technique called electrospinning to create these fiber structures that can hold and then deliver these very complex biological payloads. And the critical finding from the research is that the specific drug they incorporate, in this case the surene complex, it actually changes the physical and chemical properties of the hydrophilic PVA nanofibers.
That makes perfect sense. I mean, if the fiber's job is to hold and then release a complex drug, the chemistry of that drug has to influence how the fiber itself is structured, right? You have to tune the whole system to protect and then deploy the payload.
Exactly. It just shows the incredible precision that's required. It's not just sticking a nanoparticle onto a textile, it's designing a delivery vehicle at the nanoscale.
So the functionality, whether it's shielding from X-rays or anti-counterfeiting or drug delivery, it all hinges on this incredibly precise nanoscale chemistry, which I imagine makes the manufacturing and the scaling up process an absolute nightmare for consistency.
That is the perfect segue. We have to shift our focus from what these materials can do to how they're actually made. That brings us to the role of fabrication techniques. And electrospinning really stands out. It's this massive critical field for creating the very structure of these advanced nanomaterials and textiles.
So how does electrospinning work exactly? And how is it used to make these functional materials like the filter materials you mentioned?
In essence, electrospinning uses a strong electrical charge to pull incredibly thin threads, nanofibers, from a polymer solution. These fibers collect on a surface, and they form a mat that's highly porous but has a huge surface area. This process is amazing for creating sophisticated filters because those dense, tiny fibers are exceptionally good at trapping tiny airborne particles.
Okay, that makes sense for high-end air purifiers or maybe specialized lab filters. But the research really emphasized how much effort is going into perfecting the process itself.
Yeah.
Why? I mean, if the concept works, why are they so focused on the machinery?
Well, the challenge for mass application is all about consistency and speed. You can make a perfect sample in the lab, but for industrial scale, you need total uniformity. Otherwise, your filtration capability or your drug delivery capability is going to fail.
So what specific research efforts did you see on optimizing the industrial side of this? Are they just making small tweaks or building entirely new systems?
It's a bit of both, but with a huge emphasis on achieving homogeneity at scale. For instance, there's a lot of research into the uniformity of needleless electrospun nanofiber mats. Needles are great for control in the lab, but for mass production, you want a system that can spray or spin huge amounts of this material at once. And maintaining consistent fiber size and mat density in those systems is incredibly difficult.
So the goal is high output, but without losing that nanoscale precision.
Precisely. We also saw optimization efforts for specific uses, like tuning centrifugal spinning parameters. That process uses rotational force instead of an electric charge to create the fibers. And researchers were specifically looking at creating polybutylene succinate nanofiber mats for aerosol filters.
Polybutylene succinate, that's a bit of a mouthful, but that's a biodegradable polymer, isn't it? So why tune the process for that specific material? Does every different polymer need a whole new manufacturing setup?
They are constantly optimizing because every polymer and every end use has different requirements. In that case, they used polybutylene succinate because it's more environmentally friendly. But optimizing the centrifugal spinning ensures the fibers have the right size and structure to effectively filter out aerosols, which are, a very common pollutant.
And what other manufacturing tweaks are happening?
Well, there are investigations into electric field homogenization in radial multi-nozzle electrospinning systems. Again, that's all about getting reliable, scalable uniformity. And finally, these nanofibers aren't just for making new fabrics from scratch, they're also being used to improve existing ones.
How so?
We saw research on using these nanofibers to reinforce textiles, specifically to stop crimping and improve the structural integrity in laminated textile composites. Think about high-performance gear or maybe composites in vehicles. This nanolayer acts like an invisible scaffold, making the whole material stronger from the micro level up.
We started this deep dive focused on textiles clothing, bandages, filters. But the research you shared shows the utility of nanomaterials goes way beyond just functionalizing fabric. Let's expand the scope a bit, to go beyond textiles and into some of these cutting-edge components.
This is where we really start to glimpse the future, where material science and electronics intersect. There were two really advanced concepts in the research that show this breadth. First, the possibility of producing organic chips.
Organic chips, that sounds like something straight out of science fiction.
Well, it's quickly becoming reality. The research focuses in particular on nanocellulose-based transistors. Now, nanocellulose comes from wood pulp or other plants. It's a renewable, widely available resource. And by using these fibers, researchers are working toward flexible, bio-friendly electronic components.
So we could eventually have processors and sensors that are built right into biodegradable materials or maybe disposable medical devices. What was the second advanced concept?
The investigation of the electrochemical performance of coal-derived carbon nanofibers, this is about utility across industrial sectors, really, specifically for things like energy storage or advanced battery components. It just shows how the research output from these textile-focused fabrication methods is now spilling over into major industrial challenges, like energy density.
I also want to highlight an environmental application that provides immediate value outside of clothes or batteries. The research looked at dye removal.
Ah, yes. Using functionalized nanofiber membranes, specifically a contosin graphene oxide combination, to remove common industrial dyes like methylene blue and Congo red from wastewater.
So these highly specialized nanofiber mats, which we first talked about for air filtration, are also being designed to actively clean up heavily polluted water. That's high-level chemistry on an industrial scale.
It is. The huge surface area and the tailored chemistry of the nanofibers make them incredibly efficient at absorbing these contaminants that are usually very hard to remove.
Which brings us to a really necessary counterbalance. As much as we celebrate these technological leaps, the research community is also highly focused on a critical balance. We have to investigate the potential disadvantageous effects before these things become, well, ubiquitous.
Absolutely. When you're dealing with matter at the nanoscale, the implications for safety and the environment can't be an afterthought. This isn't just about making new products. It's about responsible deployment.
So what's the most prominent environmental issue that the sources raised in terms of everyday use?
The big concern being studied is the release of so-called nanoplastics from these textile products, during washing and just everyday wear and tear. When these advanced fabrics abrade, tiny nanoscale particles, way smaller than microplastics, are released into waterways. And researchers are really trying to understand the full scope of that release and its long-term impact on ecosystems.
That really complicates the environmental benefit of some of these materials, doesn't it? You might have a biodegradable polymer, but if it's constantly shedding nanoparticles, that's a whole new problem.
Precisely. And on the health side, the research is just as vital for ensuring safety, both for the person wearing the garment and the worker handling the materials.
And what specific research is going on to ensure things like skin safety?
There's ongoing research into the in vitro skin toxicity of the nanoparticles themselves. The sources specifically mention studies into common antimicrobial agents like copper oxide and zinc oxide nanoparticles. These particles give you that great antimicrobial coating, but researchers have to be sure that repeated long-term skin contact is completely safe. It just underscores this intense, necessary focus on responsible testing before these technologies get a global rollout.
What really stands out to me is how comprehensive this whole field is. We started with ancient cotton, and we've ended up with anti-counterfeiting luminescence, drug delivery nanofibers, and the environmental challenge of nanoplastics. The pace and complexity are just undeniable, and the impact on everyday products, from our clothes and safety gear to medical supplies and industrial filters, is clearly growing fast.
It's staggering. The progress in using nanomaterials to either radically improve existing textiles or to create completely new functional properties it's defining the next generation of material science. And what's fascinating is that the editors of the source material themselves admitted that because the field is so broad, it goes from flame retardancy all the way to nanocellulose chips, it was nearly impossible to cover all the relevant aspects in just one volume.
So even they realize they're only scratching the surface.
Exactly. They're already considering a second special issue just to keep up with the breakthroughs happening right now. So here's the final provocative thought for you to consider. If a textile can clean water, monitor your health, and deliver targeted medicine, what happens when your daily wardrobe becomes your own personal diagnostic lab? How quickly do you think these rapid lab breakthroughs will move from specialized research into revolutionary, everyday items in your life?